Hello and welcome to a lecture on interference and reflection of waves. All right, so this is going to be a brief lecture that is just going to introduce some ideas that we're going to see later on for sound and light waves, right? And as well as waves on a string, especially involving one part of the law of reflection. Right? We have a very straightforward objective here. We just want to introduce the law of reflection and the principle of superposition. Okay, so let's look at our key terms. All right, so first of all, we've got the law of reflection in two parts. Okay, so the law of reflection says that a reflected wave has an angle of reflection equal to the angle of incidence. So this is your incident wave traveling here with the wave represented in green here. Then when it hits a surface, it gets reflected off like so, and the angle as measured with the direction called the normal direction, all right, which is just perpendicular to the surface, must be equal upon reflection. So in other words, theta I, the angle of incidence, equals theta r, the angle of reflection. Okay? So if the wave came straight in, it would get bounced straight back off, because in that case, it'd be 0 equals 0. All right? And the idea here is that these lines are what are called rays, which is really helpful for tracking waves. This will be particularly important for discussing light as a wave later in your study of physics. Okay? Next, we have the second part of the law of reflection, which is more relevant for a standing wave on a string, which is something that we'll talk about when we talk about stringed instruments and how they relate to sound. Okay? And here we have a wave colliding with a rigid boundary, a fixed in, causes that wave to be inverted. And this can also apply to sound waves and tubes, by the way, like a tube instrument. So here we have just a simple case of just imagining one half of a wave pulse, just basically a crest, traveling at a certain velocity and then hitting a wall, right? That's our rigid boundary or fixed end. After the reflection, notice what happens. The wave gets bounced back, and we're assuming no loss of energy, so it's a perfectly rigid wall and of infinite mass. And as the wave gets bounced back, it gets inverted. It goes from being a crest to becoming a trough. Okay? So that's the idea. That's what happens with reflection. Okay? Next up, we have the principle of wave superposition. Okay? And this says that when two waves coexist at the same time and location, their displacements add together. So you would take whatever is their vertical displacement if it's a transverse wave, or you would take whatever is the pressure variation if it's a longitudinal wave, and we'll talk about that more when we talk about sound. But the point being is that whatever is the effect of the wave, you simply add it together when two or more waves coexist at the same place in the same time. All right? The idea there is that waves don't collide with each other because waves don't actually carry the medium through which they travel with them. They just displace the medium, but the medium doesn't have any net movement. The wave will continue on with a certain velocity, but the medium won't. Think about the ocean wave and the seagull if you've seen my previous lecture introducing waves. Okay? So that's the idea. That's why we call it wave superposition, a word we've never used in our discussion of the physics of mechanics before, because it is unique to wave. It's unlike, say, colliding particles, because waves are not particles. They are a separate physical phenomenon. All right? And a couple of clarifying points about wave superposition. This creates what is called interference, this idea of wave superposition. Constructive interference is when two waves are in phase, and destructive interference is when the two waves are half a wavelength out of phase. Okay? So it's important to mention interference because that's usually what we refer to when we talk about waves coexisting. We use the word interference. So you can think of interference as being a consequence of the big idea of principle of wave superposition. Okay? But in practicality, it's almost we always talk about interference, constructive or destructive. And with that in mind, we should get to our first practice problem here. All the practice problems will just be conceptual questions. There are no computational questions with this material because really we're not going to use it until we talk about sound and light later on. Sound coming up soon, light later. Okay? All right, so let's do our first practice problem. Question 1 in 3 parts, A, B, and C. And question 1 is all about imagining two wave sources, right, that are then spreading out, all right? So you could think of this as dropping two identical pebbles into a totally placid pond and watching the ripples spread out over each other. And as those ripples interact, we're going to get wave superposition. So we're going to use a dot in part A to draw 5 locations of fully constructive interference between the two traveling waves. Okay, so this is where the waves are in phase. All right, so you can see, I'm going to zoom in on this. There are points where they're in phase, where a crest overlaps a crest, or where a trough overlaps a trough. Okay, and what I mean by that is I want you to imagine these black lines as being the crest of the wave, which is the intuitive way of thinking of it, and halfway between every crest is a trough. Okay, so in other words, if we were to go up here and kind of zoom in further, we'd imagine that the wave would look like this. Right, there'd be crest, right? And then trough and a crest, okay? With equilibrium points in between, and then the crests represented on each black line, and troughs exactly halfway between each black line, all right? And then a full wavelength would be the distance between two crests. That would be one wavelength, okay? All right, so we can have constructive interference, which makes extra deep troughs, and constructive interference that makes extra tall crests. And those crests would just exist for a moment in time because then they would just continue to travel on, okay? Now we're going to draw at least 5 locations of fully destructive interference between the two traveling waves. All right, so here we need to have a phase difference that isn't 0. We need the waves to be out of phase. Specifically, we need them to be half a wavelength out of phase or pi radians out of phase. All right, well, that's going to occur wherever a crest overlaps a trough, right? So for example, here we have a trough of wave source 2 overlapping with a crest of wave source 1, right? And I drew examples of many such crossing overs of troughs and crests, okay, where they coexist. And then finally, just to be clear, not everything is perfectly destructive or constructive. Obviously, there's everything in between where the phase difference is, say, pi over 6 radians or something, or just even pi over 2 for that matter. In that case, you have partially destructive interference, and you can see that would just happen anywhere that is not a crest overlapping a crest, a trough overlapping a trough, or a crest overlapping a trough, all right? So for example, over here in the corner, right, here we have another one, right? These are all examples of partial destructive interference. And to highlight that point, we can imagine this one here, right? Because this right here would be a point of total destructive interference. This crossing of crests would be constructive. And you can see right between the two is the partial. All right? Okay, so let's move on to our next concept question. Here, we're going to do something quite similar to the previous one, the question 1, but instead we're going to consider a wave looking at it from the side rather than the bird's eye view of the ripples. So two sinusoidal waves traveling in the same direction have the same frequency, but they have amplitudes A1 and A2, which I'm going to assume are not going to be the same. What is the smallest amplitude of the resultant wave, and what phase difference must the waves have to create this smallest amplitude? Okay, because they're traveling in the same direction, they have the same frequency, so they're going to coexist, right? So here are the two waves, all right? Wave 1 with amplitude 1, wave 2 with amplitude 2. I'm showing a vertical displacement of the wave. I'm assuming it's a transverse wave, maybe like an ocean wave or a wave on a string. The waves are going to have different velocities, but we don't care what those are. We'd have to know the tension and linear density of the string if they were indeed waves on a string in order to find that velocity. And I'm drawing the waves as functions of position, and I could have drawn them as functions of time, but I chose to draw the waves as functions of position. Okay, so now let's imagine what happens when those waves coexist. Well, if they coexist in such a way that they're going to have the smallest possible amplitude, well, that means that we need them to cancel out as much as possible. So we need wave 2 to be a crest when wave 1 is a trough, and vice versa, okay? And then the sum of the two waves will be the green wave, which is A prime, okay? All right, and notice that A prime is not just flat because the amplitudes are not the same. If the amplitudes were the same, they would completely cancel out. All right, but instead, A prime has a value, its amplitude value, right, measured in meters because it's on the vertical axis, would be A1 minus A2. All right, and of course that is only possible when the phase difference is pi radians, okay? Now notice I've described the phase difference as both half a wavelength and pi radians. That's two ways of saying the same thing, okay? Because, we're talking about the waves, either being or being out of phase in terms of a full cycle being 2 pi radians, or being out of phase in the sense of a full wavelength being, lambda or 1 wavelength. Okay? Well, what if we wanted them to have the largest possible wavelength, all right, or amplitude, excuse me? Well, in that case, we need them to be in phase. Here they are, drawn in phase. And in this case, we have a resultant wave that is that is taller than either because it's the sum. It has equilibrium points at all the same, right? Its crests are exactly lined up and its troughs are exactly lined up because everything's in phase. Okay? So here, the resultant amplitude, A prime, is the sum of the two amplitudes of the original waves, and the phase difference is 0 radians. Okay? All right, so our last question is going to look at the idea of reflection, okay? So here we're going to look at a traveling wave that is described by this function, right? This is the mathematical form of a traveling wave, a function of both position and time. So what happens when that wave hits and is reflected off a fixed end of a string, right? Like a rigid wall. How would we represent the function in that case? Well, the way we represent it is by putting a negative in front. The negative represents the inversion. The negative represents what phase change? A phase shift of, you guessed it, pi radians, right? Because the reflected wave is exactly 1/2 repetition or 1/2 wavelength out of phase, okay? So that negative is that exact opposite wave, which is what happens. That's what inversion is. Inversion is another term. It's a specific term to reflection, but it's another term for a phase shift of pi radians. And that's going to be important because that's going to allow us to understand what happens at that fixed in reflection point, which we will call a node. But we'll do that in our chapter of standing waves on strings when we discuss sound. Well, I hope this introductory lecture, a short conceptual lecture on wave superposition and interference, has been interesting and informative. Thank you so much for watching.